article. So this article is related to multiscale numerical investigation of buoyancy-driven nanofluid heat transfer with practical particle scale transport effects in MATLAB. So here is basically the study of multiscale numerical investigation of buoyancy-driven heat transfer in an A1203 water 1 nanofluid and confined within a square enclosure as well. So the incompressible Navier-Stokes equation with the uh, Boussinesq approximation are solved alongside the energy equation using a finite difference scheme as well. So the nanoparticle migration leads to speciality. Leads to spatially non-uniform conductivity enhancement, significantly influencing heat transfer characteristics. So, in the introduction, I have just detailed explained that how the electronic cooling, solar collectors, heat exchangers applications are used in this particular nanoparticle distribution, and how temperature field with velocity vectors are correlated to each other, and how we can check with the nanofluid in multi-scale simulation according to flow and thermal matrices, heat transfer performance evaluation, 3D temperature distribution, thermal conductivity enhancement, vorticity field, heat flux according to temperature field, stream function with streamlines, and the nanoparticle distribution as well. So the background and motivation is written limitation of existing modeling approach. According to the realistic system, nanoparticle undergo the migration due to Brownian motion fluid advection and buoyancy-driven circulation as well. Okay. So the multiscale particle resolved through modeling. Basically, we have just added the particle distribution directly influences local effective properties of the nanofluid, and the local variations can significantly alter temperature gradients, velocity fields, and heat flux patterns as well. Okay. So these are the objective with the thermal coupling, flow thermal coupling, importance of local property variations with the visualization and multi-field analysis as well, the relevance to engineering applications, and the novelty and scientific significance. When you will read this, you will understand like what I'm talking about and what I'm trying to provide you everything accordingly. Okay. The problem statement with the mathematical approach is provided as the continuity equations according to the mass conversion, and these are the incompressibility of the nanofluid. The fluid momentum is basically governed by the Navier-Stokes equations. So these are the equations, and the temperature evaluation as well. So the nanoparticles are Lagrangian equations, and these are the Stokes-Einstein's relation equation. This is the thermal conductivity equation. This one is also the boundary conditions accordingly. The heat transfer methodology provide us the physical properties of fluid and nanoparticles. And next one is basically the derived thermal and flow matrices as well. Okay. So the MATLAB simulation and analysis as well. These are the parameters used for MATLAB simulation and parameters. And next one is the temperature field final according to the nanofluid domain. Next one is velocity magnitude with vectors. Next one is stream function with streamlines. Next one is nanoparticle concentration as well. Heat flux magnitude and direction as well. This one is vorticity field output graph, thermal conductivity enhancement, and next one is the Nusselt number evaluation, temperature evaluation, flow and particle matrices, results and discussion according to the sample simulation results, according to different values of temperature, velocity, effective thermal as well, conclusion and references. Let me just provide you the output. Multiscale. These are the output results for the simulation as well. When you will run it, you will get the output results accordingly. See, temperature field, final time accordingly 3, velocity magnitude with vectors, stream function with streamline, and output results accordingly. Okay. Thank you. If you need to ask anything, you just ask me. I will answer your questions. These are the MATLAB code. Let me explain to you what I have happened. And this is a function of nanofluid simulation separated plots. These are the commands to display. And next one is simulation parameters. These are the parameters defined here according to different comments. All the comments are added like length, height, grid points, x, y, z. These are the footprint for the f print means printer of the number of nanoparticles according to the simulation parameters. And we have just printed the parameters. And next one is these are the initialization of simulation according to the grids. And I have initialized the temperature field, then initialize the velocity field, calculate the effective properties according to the different equations of k coefficient and k efficient and the mu efficient as well. So these are the fluid components which used in the paper I have explained to you. And initialize the nanoparticle positions, track nanoparticle concentrations, then initialize the result storage and main simulation loop as well, in which I have added the while loop which just provided the current time less than the parameter dot total time. Then the current time will be less than the total time, then the loop will in running condition and it will display the times accordingly. And it just the time logic is step is equals to step plus 1. It means a step or previous value plus 1. Okay, so it goes to the next state. According to same, it added the store time with the step 1 according to update nanoparticle distribution, calculate local properties, then solve flow field and solve temperature field. These are the equations used for different solution of fields and boundary conditions. Then I have added the calculate the matrices, store matrices. These logic used for store matrices. Post processing name, we have just added the here fprintf command, like the plots are in calculating and getting the plots in terms of MATLAB. So these are the time vector defines here, these equations, and these equations calculate the derived vectors, derived fields, and these are the separate plots for the six separate according to different time average and x, y, t, u. Basically, these are the time parameters and as well as the velocity, psi, and everything. Okay, so these are the results accordingly as well. And the print summary, and then the print summary. These are the summaries. Function defined. These are the functions I have defined for nanoparticles. Brownian motion coefficient, current position, nearest grid cell, get velocity at particle location, Brownian motion equations, update position, apply boundaries. These boundaries applied, update density field, then normalization of the density values. These are the second value or second function used for local properties according to thermal conductivity, density, temperature effect, solid flow field, and buoyancy force Laplacian. These are the Laplacian equation I have used in it. Convective terms, these are used the convective terms. Equations from the previous equation to update the equations, then solve the temperature field function, and the solve temperature field I have defined all the parameters, then thermal diffusivity, Laplacian convective terms update, and then apply boundary conditions, left wall, right wall, top wall, bottom wall. Next one is calculate matrices, Nusselt number at hot wall, other matrices according to the limit values. Then calculate the stream function. This is a stream function for calculating up left bottom and left corner. Then I have added the function for the heat flux function. These are the parameters used for heat flux function. Velocity, calculate the vorticity function. These vorticity function defined, and next one is the separate plots for the different temperature field, different at different time, with the velocity vectors, with the magnitude, velocity magnitude with vectors, as well as the streamlines with the stream functions, and creating the plot 4 by 9 nanoparticle distribution accordingly. Nanoparticle concentration, creating plot 5 by 9 heat flux, as well as the heat flux magnitude. All the plots are added according to the titles are given here. Like these are the titles given, and you just read it, you will understand like what plot is this. Okay, so this is the end of main function. Okay, so if you need to ask anything, you just ask me, I will answer your questions. Thank you.